Today's video is going to take a look at how to graph quadratic equations using vertex form. And you did a Desmos activity which was focusing in on how to identify transformations, like what does the a, h, and k value do. So what this video is going to do is summarize those things and be able to look at one example that's given below and be able to describe transformations, be able to identify additional points, find some characteristics, talk about max and mins, x and y intercepts, those types of things. So we saw so far that vertex form of an equation looks like this: a times x minus h squared plus k. Now, without that squared there, this would not be a quadratic. Without that squared there, it would not graph like a parabola, the U shape that we get whenever we graph a quadratic equation. So it has to be there. You cannot forget about that piece. But these three values, a, h, and k, are going to do three different things for our graph, okay? We know about quadratic functions. The most basic form, x squared, is centered at 0, 0. We call that the vertex, okay? So if it's centered at 0, 0, and that's where the vertex is of x squared, if we can identify where it's moved, either left, right, up, or down, and maybe the shape of it's changed, if it's gotten a little bit skinnier or a little bit wider, we're able to identify what our graph should look like. So when we look at these three things, the first thing we can note is this k value at the end. This is going to account for our vertical shift. It's going to move our graph up or down. So if you see a +2 at the end, it's going to take that whole entire parabola and move it up 2 spots. See a -5, it's going to take the whole parabola and move it down 5 spots. But think about how that relates to the vertex. It's going to move the vertex not at 0, 0, but let's say it's a -5 there. It's going to shift this whole graph down 5 spots, and it's going to now change the location of the vertex to 0, -5. Okay, so take a look at this value here, h. The h value, the number inside the parentheses, which is closest to the x and within the quantity being squared. H value is going to account for our horizontal shift, which means it's going to move it left or right. But what you got to be careful here is it actually does it the opposite direction that you would naturally think. What I mean by that is this. Let's say we have our equation x minus 4 squared minus 5. We said that this is going to move it down 5. But this -4, you think -4, you're like, oh, it's going to move it left. It doesn't move left. It actually moves to the right 4 spots. It's one way to think about it is it's the opposite of what you see, but also it's the value that actually makes this quantity 0. Like if I plugged in a +4 for x right here, 4 minus 4 is 0, so it moves it to the right 4. So we know that this is going to move it opposite of what we would think, right 4 spots. So now the vertex is down 5, right 4. It's actually right here at the point 4, -5. So we can identify the vertex by looking at these two values because that's our horizontal shift and our vertical shift. So we can find our new center. And then from there, our final part here, this A value. We refer to this as the vertical stretch or vertical compression. A more general term is it's the dilation. It's the shape changer. Is it going to make it skinnier or wider? Okay. If our A value is negative, if it's a negative value, that means it's going to reflect it. So it's going to flip it upside down. It's going to be a reflection. So we can have a dilation, which is going to change the shape, where the A value is going to vertically stretch it if it is greater than 1. So for example, 2, 3, 4, 5 in front of it is going to be a vertical stretch because it stretches it vertically and it makes it skinnier. Okay. If the value of A is in between 0 and 1, like a 1/2, a 1/3, a 2/3, that is going to be a vertical compression. It's going to flatten it out and it's going to widen out the parabola. So we can kind of identify what's taking place with our transformations. So for our first example, let's identify the transformations and characteristics. So the first thing that should stand out is there's a 3 in front. That is a dilation by a factor of 3. To get even more specific, we call this a vertical stretch. It's going to vertically stretch it. It's going to make it skinnier, okay? We also see that there's a +2 there. That means it's going to move not to the right 2, but left 2, a horizontal shift, you could say. And this -8 means it's going to move it down 8. You could say a vertical shift down 8. So where's the vertex? These two values here, if the vertex is usually 0, 0, it's not anymore. We know it's moving to the left 2 and down 8. Left 2, down 8. 1, 2, 3, 4, 5, 6, 7, 8. I guess I could have known this is a 10 by 10 square and counted up instead. That would have been easier. So our vertex is at the coordinate -2, -8. So we have our vertex identified. The question is there going to be a maximum or a minimum? So a maximum, remember, is going to have this shape for a parabola, where there's a peak, there's a high point. A minimum is going to have this shape for a parabola, where there's like a valley, a low point. So our graph is going to be our standard U shape, like this, because the number in front is a positive. So there is going to be a minimum at the vertex, -2, -8. That's where the minimum is going to take place. Now, if there was a negative in front, flip it, and now there's going to be a max. So here's what we have to do, graph our function. So we know it's going to look something like this, and I'll delete this in a second, but it's going to look something like this. But we need exact points. If on the test you just do that, you're not getting a whole lot of credit. But we have a general idea of where it should go. So here's what you need to do. You need to include the vertex, but also a couple additional points, like 2 additional points to the right or 2 additional points to the left. Because parabolas are symmetric, what's happening on one side of the vertex is also happening on the other. There's what's referred to as this axis of symmetry. This line that kind of is like the mirrored image across from it. And we'll get to that in just a second. But let's create our table. And our vertex is located at -2, -8. So if we want to create some additional points, what we need to do is just choose some x values near it, plug them in, and see what we get back. So we have an x value of, let's find out what's happening over here to the right. So let's choose an x value of -1, and then let's also choose an x value of 0. And then we can plot those points and see where it's going. So if I choose an x value of -1, we actually have to plug it into our equation all the way up here. So let me just show the work off to the side. It would become 3 times, not x, -1 plus 2 squared minus 8. Now here's the thing, you got your calculator, you can feel free to type that in. Use your parentheses appropriately, or this is something we could definitely do mental math on. Just follow your order of operations. You have a set of parentheses here, so let's simplify that. 3 times -1 plus 2, that's just 1, squared minus 8. Well, continue your order of operations. Now you do your exponent. 1 squared is 1. 3 times 1 minus 8. Do the multiplication now. 3 times 1 is 3 minus 8, and we end up getting -5. Okay, so we're right here at -1 all the way down to -5. 1, 2, 3, 4, 5. Okay? The next one we have to do is 0. If I plug a 0 in, substitute in 0, we would get, and we can just do this mentally, if you plug in a 0 right here, 0 plus 2 is 2, square it to get 4. 4 times 3 is 12, but take away 8, we are at +4. So I'm over at 0 up to +1, 2, 3, 4. So the reason we only need 2 points, additional points to the right, is because parabolas are symmetric. What's happening on one side of the vertex is happening on the other. We can go equal distance from the center directly across, one spot over, one spot over. They're going to be in the same location. 2 over, 2 over. It's always going to have that symmetric shape. So when we graph this, notice how narrow this is. And I'm probably going to struggle graphing with this tablet. It's actually okay. So far, I guess I shouldn't speak too soon. Got to finish the other side. Okay. Notice how this parabola is way more narrow than our standard x squared. It's because it's stretched vertically by a factor of 3, right? So let's get to a couple more characteristics. I'm actually going to skip over x-intercepts for right now. Sometimes we'll be able to find them very easily on our graph, but right now you can see they're here and here. We're not going to approximate them. We'll solve for them kind of later in this unit, potentially next unit, so we'll skip that for now. The y-intercept, though, we should always be able to find. A y-intercept is where it crosses the y-axis. And very conveniently for us, we can see it. 1, 2, 3, 4, 0, comma 4. Now, what we could have also done is we could have solved for y when x is 0. You can always plug in 0 to equation and you will always get back the y-intercept. Plug in 0 for x, you will get back the y-intercept because notice the coordinate. The x value is 0. So shouldn't it make sense if I plug in 0, it gives me back the y-intercept every time? Yes, exactly. Okay? Axis of symmetry. That is this vertical line that cuts through our graph, which will always pass through this vertex. It'll always pass through it. So this is at an x value of -2. So the axis of symmetry is x equals -2. I mean, if you remember if you were to graph x equals -2, it would be an x value of -2 and it would be a vertical line. So that's why we write it like that, because that's just the equation of a vertical line. X equals. The domain is the concept of what are the x values that work for the function. So domain is x's, range is y's. So when you think about domain, you can think about it two ways. You could think about it in terms of what are all the x values you could plug in to your equation and get something back for. Or what are all the x values you could substitute in and not get an error? Well, in this equation, it was 3 times x plus 2, what was it again? Squared minus 8. I could plug in any x value here and I'd be able to enter in my calculator, hit enter, and it'd be fine. So our domain is all real numbers. All numbers work. Okay. Another way of saying that is this. Here's a shorthand notation. It is an R with 2 lines. That's the symbol for all real numbers. It's like that new paragraph symbol in proofreading where you do the P with 2 lines. That's what this is, all real numbers. Okay. The other way to write it is using what's called interval notation. When we look at our graph and I'm looking at domain, you kind of follow the arrows. Okay. Domain is x's. So I don't care that this graph is going up. Who cares? Doesn't matter. If I'm thinking about x's, I'm thinking about side to side, right? That's our x-axis. So if I'm thinking about x's and I'm thinking about side to side, and I'm thinking about what are all the x's that are graphed, well, imagine continuing those lines on forever, right? Yes, it's going up. Who cares? Doesn't matter. What's happening though is it is continuing to move out. It's continuing to move further to the left and further to the right forever. So if that's happening, it's really taking up every single x value you could ever think of. Forever to the left, we call negative infinity. Forever to the right, we call positive infinity. So what could we say? From negative infinity to infinity. Now the range are the y values. So when we think about y values, we think about what are the numbers we could actually get back. So now we don't want to think about this side to side. We want to think about this vertically. So when we're looking at the y values, we think about what are all the y values that are graphed. Well, here's a y value of 4. Here's a y value of 0. Here's a y value of -5. Here's a y value of -8. But then notice what happens. It shoots back up again. So when I look at my graph, there is never going to be a value graphed below -8. Okay, so how do I represent my statement now? If I know it's from -8 is the lowest, and it goes, look at the arrows, it goes up forever. What we're gonna say here is that the range of this graph is all of the y values that are greater than or equal to -8. Now, if we want to be consistent, though, with this notation, interval notation, we could say least to greatest. It goes from -8 as the lowest, and then the highest, think about y's. Infinity is up here for y's. Negative infinity is down here for y's. It goes from the lowest being here, and notice how it goes up forever. Forever up. Think about as it continues to increase forever, it's going all the way to infinity. You always write them from least to greatest. So a lot going on here in these final two characteristics. We will definitely practice this more in class. This is just trying to summarize what you saw in that Desmos activity. We know what A, H, and K now represent. We can account for our transformations, which leads to our vertex, understanding the shape of it, either facing up or facing down. And from there, we can plot points, use our axis of symmetry to reflect it across, get a good shape for our parabola, and then answer some extension questions. Okay, that's it for today. We will practice this in class next time.